Calculus, the main yet intriguing part of mathematics that is seen everywhere. Economics, physics, even in analysing football players and their formation. There's so much to learn and discover in calculus given how integral it is. Speaking of integrals though, that's what we're going to focus on today. Finding volume of revolution through integration with food. We're going to start by illustrating the graph and we'll stick with the xy Cartesian axis. Let's take the basic graph of y equals to 3 and we rotate this region about the x-axis completely by 2 pi radians or 360 degrees. You notice that we obtain a circular container and we can represent it with a Swiss roll. We want to find the volume of the cylinder. Obviously, we can simply use pi r squared h for this case, but another way to find the volume is similar to serving a Swiss roll and have this smaller circular disc, which is the idea and name of the method to find the volume of revolution, the disc method. The main idea is obtaining many discs and add the volumes of this circular disc to obtain the volume of revolution through the disc method. However, there are some issues to consider with regards to the disc. Let's say we have the graph of y equals to x squared for x bigger than or equals to 0, and we rotate this region completely about the x-axis. We obtain a shape similar to a frustum or a halved lemon. We can already see that not only will we obtain discs of varying radii, we will also have imperfect discs, where the radius on one side is not the same as the radius on the other, and we also get a non-uniform height. As such, we can't immediately use pi r squared h as A, we don't have perfect discs, B, it results in either an over-calculation or an under-calculation of our volume depending on the radius you chose. Yet, we can rectify these issues using the theory of calculus. If we have to reduce the thickness of each disc, the radii on both sides will get more and more equal. Eventually, the disc transforms to a circular line and has negligible thickness, and now the radii are equal on both sides. With this circular line disc, we also resolve the issue of obtaining an over or under calculation as the width is now a point. The upper and bottommost points would perfectly touch the surface of the revolution, giving us the exact volume. As such, we can have infinitely many more discs at every point since the thickness is negligible so that we can cover all the points on the graph. And the volume of all these discs would give us the volume of revolution with the disc method. We know that the volume of the disc is pi r squared h, and we need to find the radius and the height of the different discs. Let's start with the h, the thickness. As you can see, it's the difference between these 2 points that are horizontal from each other, thus the difference is in their x coordinates delta x. Since you want the width to be incredibly small and negligible to obtain a circle, delta x will be very close to 0, hence we have delta x approaching 0 and obtain dx, indicating a vanishingly small width. Therefore, h equals to dx. Now, onto the radius. Looking at the disc, their respective radii stretches vertically upwards from the x-axis and to the graph. Since the point on the graph is given as xy, the radius is simply y. And we then have the volume of one disc as pi y squared dx. Similar to the Riemann sum integral where we add infinite number of negligible width rectangles and obtain an integral, we add all the volume of the disc with negligible width and obtain integrating pi y squared dx for finding the volume of revolution about the x-axis with the disc method. Similarly, if we were to rotate about the y-axis instead, we will obtain the figure of the lemon or Swiss roll facing upwards. We see that the width of the disc will now be dy and radius will now be x. Volume of one disc will now be pi x squared dy. And using the same earlier explanation, we have integrating pi x squared dy for finding the volume of revolution about the y-axis with the disc method. In conclusion, the disc method obtains perfect circular discs from revolved figures such as these. Rotated about the x-axis, our figure will look like this. Each disc has radius y with dx, hence volume is integrating pi y squared dx. Rotated about the y-axis, our figure will instead look like this, facing upwards. Each disc has now radius x with dy, hence volume is now integrating pi x squared dy. So there we have it, the disc method explained through a Swiss roll and a lemon. Bon appetit!